Television is basically magic. Think about it. You're staring at a glowing rectangle right now, and somehow, that rectangle can show you people, explosions, drama, cars, planes, trains. Well, Luigi, how is it doing that? How on earth do you go from electricity in a wall to Breaking Bad in your living room? Well, to understand that, we need to go back to when TVs were basically magic radiation cannons. Seriously. Analog television predates World War II. They even predate modern computers, which means they had no microchips, no software, and no little processor in the back telling it what to do. It's not calculating an image, it's just happening? Let me explain. In the old days, you had the CRT TV, aka the big chunky box that weighed as much as a small car. The magic inside was something called a cathode ray tube, and the radiation cannon? That wasn't a joke. Inside the back of the tube is a heated piece of metal that releases electrons, which was appropriately named the electron gun. Those electrons get accelerated forward in the tube and crash into the screen. And for this reason, back in the day, watching TV was often called watching the tube, which also explains the name of the website you're watching this on. Now obviously, just shooting subatomic particles at glass should not produce Pokemon. You see, the inside of the screen was coated with phosphor. When the electron beam hit the phosphor, it lit up. So the TV wasn't displaying a picture all at once. It was drawing it, line by line, from left to right, top to bottom, again and again and again, like a laser beam turning on or off precisely at different points and scribbling across the screen so fast, your brain gives up and says, yeah, okay, that's Heisenberg alright. But here's the part that feels illegal. The electron beam must hit very specific points on the screen. So how do you aim a beam of electrons? Magnets. The answer is magnets. The TV uses magnetic field to bend the beam left, right, up, and down. So old televisions were basically using magnets to steer tiny charged particles around a glass box in your house. But wait a minute, how does the TV actually know when to turn the beam on and off? And more importantly, how does it know what image to draw at all? As mentioned, the TV isn't thinking and there's no computer inside to code for precision. So where is the information coming from? Well, it's being sent live as a signal. Back in the day, TV stations would take a camera feed and convert it into an electrical signal, and that signal basically told your TV exactly what to do, how bright each point should be, and when to move to the next line. The signal itself was just a radio frequency that feeds input to the complex analog circuitry of the TV and changes the strength of the electromagnet to control the scribbling across the screen, as well as the voltage of the electron gun. Higher voltage means a brighter pixel, lower voltage means a darker one. So, as the electron beam scans across the screen, the signal is constantly telling it bright here, dark here, bright here, millions of times per second. But now we've got a bigger question. How does the camera create the signal in the first place? Well, the camera used something called an image sensor tube, which basically did the same thing as the TV, but in reverse. It scanned the scene line by line using electron beams, just like the one in the TV, except in this tube, instead of the screen glowing, it had a reflective material which would bounce back the electron beams. The reflected electrons would be picked up by a sensor at the back of the tube. So instead of drawing a picture with light, it was measuring how much light was entering the camera lens. Bright areas on the camera lens would create strong signals. Dark areas created weaker ones. So the camera turns an image into a flowing electrical signal, and the TV turns the signal back into an image. It's basically copy and paste, but with electricity. And as for sound, the TV was also equipped with a radio, which would pick up the live sound from a microphone and play the sound at your home like a regular radio at the time. And so you might be thinking, if the only way to see the video and hear the sound was with a live broadcast directly from the studio to your home, that just sounds like a glorified walkie-talkie but with video. And well, yeah, that's exactly what television was in the past. I mean, the word television literally means vision at a distance. So how did they record TV shows to broadcast for later? Simple. They would shoot everything on a film and record the sound on a vinyl, and when it was time for broadcasting, they would play the film like a movie at the cinema and point the TV camera at the screen and play the audio from the vinyl. And all of that is impressive, but still kind of boring because everything's in black and white. So when the masses demanded color, the engineers solved the problem in a very normal, not at all insane way. They added more electron guns. Instead of one beam, you now had three, one for red, one for green, and one for blue. The inside of a color CRT screen had tiny groups of phosphor dots, red, green, and blue, and a metal sheet called a shadow mask would make sure each electron beam would hit the correct color phosphor. If the red glowed a lot and green and blue barely glowed, you got red. If all three glowed together, you got white, and if they all glowed in different amounts, you got every other color. That means every image on your color CRT was just millions of tiny red, green, and blue lights tricking your eyeballs. But it's the 2000s, and the new hip youth of the digital era started asking, hey, what if we didn't build a freaking particle accelerator in the living room? And so today, most screens are made of pixels, millions of them, and each pixel is usually made of 3 smaller subpixels, red, green, and blue. Same color logic as the CRT, but working with a completely different method. So what kind of a fancy modern diet did the TV go through to slim down and finally get rid of that CRT belly? Well, instead of firing electrons across a tube, modern displays control each pixel directly. Now there's a few different ways to do that, but let's start with the most common one, LCD, aka liquid crystal display. And despite the name, liquid crystals are not some magical crystal balls that show you pictures. They're tiny materials that can twist when electricity is applied. Behind the screen, there's a backlight, basically a giant white light source shining through the whole display. Then in front of that light are the liquid crystals, and in front of them are pixels. The liquid crystals twist to let more or less light through, meaning if we wanted the color red, it would block out all the light from the green and the blue pixels, and together that creates the image. So an LCD screen is basically a very sophisticated wall of microscopic blinds. The light is always there, the screen is just deciding how much of it gets through at each tiny spot. And similar to a CRT, they do this by changing the voltage. A low voltage would cause the liquid crystals to tilt slightly, blocking out only some of the light, and a higher voltage might cause it to tilt more, blocking out more light. The big difference being that instead of a continuous dimming of a laser beam based on the raw signal strength, the LCD gets its dimming information from ones and zeros that are decoded by microprocessors inside the TV and appropriately converted into the right amount of voltage to apply across different points of the liquid crystals. And of course, there's also OLED screens. With OLED, there's no backlight and each pixel creates its own light. The LED in OLED stands for light emitting diode, which is just a fancy microscopic light bulb that emits light when it receives electricity. If a pixel needs to be bright, it turns on. Like LCD TVs, it too has a mini computer on board that reads the digital video in the form of ones and zeros and converts it into the appropriate voltage. Only this time, there are no filters involved. It just turns the individual red, blue, or green pixels on, and if it needs to be black, it turns off completely. That's why OLED screens have those super deep blacks and ridiculous contrast, because black is not very dark gray. It's just nothing. The pixel is off, gone, vanished. So next time you're watching TV, just remember that we somehow managed to harness lightning, turn it into glowing dots on a screen, and somehow that turns into Netflix, which is impressive but also basically magic. Anyways, if you learned something, subscribe, and stay tuned for more atomic knowledge.